Good evening, everyone. I'm Borcherding, the head of quantum software of QUDORA Technologies, and I'm very glad that I was invited here from Robert to talk about QUDORA's QIR-Based software stack for trapped ion quantum computing. But before I start talking about the software part, let me quickly introduce QUDORA to you and tell you what we are doing on the hardware side. So, in a nutshell, QUDORA was founded in 2021 by 3 professors and 3 former PhD students. And initially, the goal was just to fabricate trapped ion chips and sell them to others so that they can build the full stack system. But now that we won a major project from the German Aerospace Center to actually build a full stack quantum computer, we hired a lot of people, and now we're more than 33 people and really cover the full range of expertise from fabricating chips in-house to building or developing software for full stack quantum computer. And we've secured 30 million of revenue so far, and what I'm particularly proud of is that we have a cloud platform that's up and running. You can register there, and you can try out one of the emulators of our partner university for free. Our main location is in Braunschweig. The software team is located in Hanover, and we also have a location in Hamburg because we're building there a quantum computer for the German Aerospace Center. And speaking of Hamburg, this is the project there. It's called Xafiro, and also the quantum computer will be called Xafiro, and it features 50 qubits, and the gates will be driven by our NFQC technology. So we call it NFQC technology because it's microwave-based, and basically all of you have in your smartphone an NFC chip, and that's where the name comes from. There's will be a SPAT qubit readout that's being developed by our partner NXP in this project, and we have to realize at least 2 logical qubits in this project. And the whole project will be finished in January 2027. In parallel, we're building a quantum computer in Braunschweig. This one will belong completely to us in the end and will be connected to our cloud platform. And besides that it looks fancy, what is remarkable here are the sizes. So it's really just 3 meters times 1.5 meters times 2 meters, and everything that we need is really inside of this housing here. And this is possible because of this NFQC technology. We're using microwaves instead of lasers to apply our gate operation, and that's why we're don't need huge optical tables here. So let me tell you now a few things about our core hardware technology. So we thought a lot about how to best explain what we're doing on the hardware level, because quantum computers are a complex machine, and we're trying to design every part a little bit better than the others. But if we boil it down, then it's really our choice of qubits and our NFQC technology that we think is unique and very interesting. So let's start with the clock qubits. So to understand the clock qubits, you have to think about an atomic clock. So if you take an atom and then shine a laser to it or a microwave source with the right frequency, then it will absorb and emit energy at a stable rhythm. And this rhythm defines the tick of your clock. And this will be very stable if the energy levels that you look at are very stable. And that's exactly the same thing that we also need for our qubits. So how do we achieve that? We apply a magnetic field to our atom, and then due to atomic physics and so on, there will be additional energy splittings, and we are choosing hyperfine ground states for our qubits. And since both of these are ground states, it's just not possible to have a spontaneous emission from the 1 to the 0 state or the other way around. So our T1 time is basically infinite. On top of that, we're choosing hyperfine states that are also magnetic field insensitive. So whenever there's some fluctuations in the magnetic field, the and I have a small animation here, the energy levels don't move towards or away from each other. And this ultimately gives you really long T2 times. A conservative estimate here is that's on the order of 60 seconds, but we think it will be much greater, maybe even on the order of an hour, but it's also tricky to measure that in the lab, I've heard. So we have qubits where we can store information for a long period of time. Now we also need the technology to apply high-fidelity gate operations. And one of our co-founders, Professor Christian Osbekaus, he was actually the first one who integrated a microwave source into a trapped ion chip and applied gate operations using that technology. And later, a former PhD student of him, who is now the CTO of our company, Giorgio, he was able to achieve a 99.6% fidelity in 2019. But this was in a university setup, and now in Braunschweig and Hamburg, we're building a much more advanced setup, and we expect to achieve much higher fidelities there. So this microwave approach is not unique in the industry. So Oxford Ionics are also having a microwave-based approach, and they have achieved an astonishing 99.99% fidelity recently. And this just shows us what the potential of this approach is. But what is unique is our choice of qubit. As far as we know, no one else is using clock qubits in the industry. So we think that in the long term we will have both the really long coherence time and the high gate fidelities. So all of this, of course, has to be integrated in some kind of chip. And I have here an example chip. I'm unfortunately not allowed to show you a picture of the chip that we are building, but this is from our partner university. There's a storage register here, a storage register here, a state preparation and measurement register here, and in this register, the NFQC technology is doing gate operations on at 2 qubits. And it's a small video. Quality is not so good because I had to compress it a little bit in order to be able to send it via email. But you get the idea. Ions are first loaded to the storage register, and then pairs of ions are being sent to the manipulation zone to do gate manipulations. So this will now take a few seconds until I think at least 3 pairs are being manipulated. So there will now be one more. And then all of the ions are being moved to the storage register again, and then ion by ion they will be measured. And this is actually being done by lasers. So we do have lasers in our setup for state preparation and measurement, but not for the gate operations. So I'm showing you all of this because I wanted to motivate what is actually important on the software side and what are our key challenges here. So as you saw, we are looking at a QCCD architecture, so we obviously have to optimize somehow the ion transport. So this is really an important part in our software. Also, we have a really long coherence time, and we wanted to make use of this from the beginning. So we had to design the software stack in a way to really enable hybrid computations. Third, even though that we expect to have really long really good gate fidelities, there will always be noise, so we also have to have a way to fight noise on the software level. And at last, everything has to be usable. We need some cloud architecture, and we have to support common languages. So these are the key challenges, and we'll now say a few words about each of these challenges and then show you how all of this fits into our software stack. So the ion transport problem can be explained quite easily. You start with the circuit here on the left side with a couple of 2-qubit gates, and on the right side you see the chip from the partner university. And yeah, you have to move the ions around on the chip in such a way that you execute the gates here in this circuit. And when we were first confronted with this problem during my time as a postdoc, yeah, the first thing that we realized was that it's actually a coupled optimization problem. So you first have to decide somehow in which order you want to apply the gates. Do you first want to start with the gate A, or do you first want to start with the gate B? And once you fix an order, you have to think about how to efficiently move the ions around for this specific ordering. Yeah, and we published a paper about this, about our approach to really tackle this coupled optimization problem. But if you add classical computations within your quantum circuit, it becomes a little bit more tricky. So here's an example circuit where you have a couple of gates, then do a measurement, and depending on this measurement result, you do another gate or you don't do the C0 gate. And the compiler would need to go over every instruction here and always has to keep track of the ion chip configuration, so of the location of the ions on the chip. And if, let's say, after the measurement, all of the ions are located here, then if M is 0, we have to apply the C0 gate, so 2 more ions have to be moved to the manipulation zone. If M is not 0, then they will stay at the storage register here. So that means that whenever we have an if condition, we double the amount of branches here. So it's really the branch explosion problem that we have here. If we have a really long problem, then the number of branches just scales exponentially with the number of if conditions. So how do we solve that? There are basically 2 ways to start here. So either try to solve this problem with a just-in-time compilation, or you try to make ahead-of-time compilation work. And initially at the university, we started looking into this just-in-time approach, where, and this might sound crazy to some people, where we do compilation really during the coherence time, because I told you we have really long coherence time. And yeah, we basically waited for the quantum computer to do the measurement, and then after giving us this measurement result, we started compiling and then sent the next instructions during the coherence time to the ions. And we actually ended up writing a paper about this, since for the specific chip from the partner university and our specific compiler, this was actually feasible, and this is what we showed in this publication. But we see a lot of benefits in just spending more time on compiling, trying out different options of the gate ordering and so on. So that's why we started looking more into this ahead-of-time approach. But unfortunately, this also comes with a price, so we have to somehow avoid this branch explosion problem, and in order to do that, we have to introduce extra movements on the chip. So whenever 2 branches appear, then you have 2 different chip configurations. And what you can do is you add additional movements here on this branch, so that this ion chip configuration just looks like this one. So that way you basically merge the 2 branches and can continue to compile. So it does come with the cost, but you can spend much more time up front to compile the whole problem. And since we're now focusing on this setup, we needed some tool that allowed us to really handle all of these branches. And that's where QIR came into our software stack, basically. Because QIR, as Lucas already explained this morning, is based on LLVM, and it actually provides you with all the tools that you need to handle and manage branches. Yeah, next is noise. We did in the last year quite some research on quantum error detection, and for that we had to develop or set up our own testing environment where we can easily refine an error detection protocol and then test it on our emulator. And our emulator really behaves like our next upcoming quantum computer, because for trapped ions you can write down the full master equation of what's going on the physical level, and all of this information really goes into our emulator. And yeah, after a while we thought it's actually quite useful for us, so maybe it will also be useful for partners, and that's why we will go live soon with this emulator and make it publicly available. We gave it a creative name. We're calling it Chameleon Emulator because the noise model we have is adaptive, so at full noise strength it will behave just like our upcoming hardware. But you also have the option to decrease the effects of noise to see maybe at which point your algorithm will start to work. And in the future we plan to make this a little bit more transparent, so that you can really see like which noise strength belongs to which hardware generation in our roadmap. It will feature also, or you can also emulate hybrid computations with that emulator, and also the decoherence effects during the hybrid computations will be taken into account. There will be QCCD and QIR support in the beginning, and you can emulate up to 29 qubits. And yeah, there's 1 hour free trial. We don't have a payment system yet, so if you need more computation time, just talk to us and we'll figure out a way to give you more. So we just want you to start the conversation with us, basically. Regarding the support of common languages, I already said we're using QIR here. And this is not a complete list, but, and correct me if some line here is wrong, but this is how it looks to us currently. So we're supporting QCCD in the OpenChasm. There's a package called QBraid, which we're using to convert them to QIR, and whatever comes out of there, this is what really goes into in our compiler. And the next language that we will support is QUDORA here. And now I am already coming here to the picture of our software stack. You have seen a couple of software stacks already today, so this is the last one for today. At the top we start with applications. These are not being developed by us. We rely here on partners, and there will also be other cloud platforms be connected to our cloud platform in the future so that you can more easily try out applications. There's a SDK that you can just install on your local machine to really connect directly to our QUDORA Cloud. And the QUDORA Cloud converts every language basically to QIR, and there we have then just LLVM passes really that do the whole work to make it compatible with our hardware. And the first layer here, the error detection and error correction layer, that's something we're actively working on now, so we just started working on. We think error detection really has to be on this LLVM IR level, because we did some research on how to, on which quantum error detection code works by just implementing them in QCCD and trying them out with our emulator. But we want this to be deeply integrated into our compiler chain so that someone with a different language could just turn it on or off. So that's where it has to live at some point. And but it's challenging because the error correction expert might not know anything about LLVM, so we have to define some great interfaces there so that it make it easy for the quantum error correction expert to define their protocols, but at the same time have them deeply connected into our compiler chain. The next layer here is transpilation. There we rely on some standard software tools, but also have a couple of custom transpilation passes that were not covered by others. And at last, we have here this optimizing ion movements pass, which also just uses our C++-based shuttling compiler, where you can also work standalone on without having to know anything about LLVM. We integrated that as a pass here. And what comes out here is our trapped ion assembly language, TIASM, and this will then go to our real-time operating system, and then, really during the coherence time of the ions, we send the ahead of time compiled commands to the FPGA, get back the measurement results, And yeah, that's our software stack. It's up and running. It is already being used when you try out our emulator, and yeah, will also soon then be used by the real quantum computers. And yeah, I have one more slide on QIR and MLIR because yeah, Lucas started this conversation today or discussion, and wanted to add something from our side. So yeah, we needed some tool to handle these branches, and that's why we really started with QIR. And it's important for us that there is at least some kind of standard. Unfortunately, it is not a complete standard. If you take some languages, convert them to QIR, the QIR will always look slightly different, but this is manageable. But it would be worse for us if there's no standard at all, because we're a small team and we want to focus on getting the most out of the hardware, but don't want to focus too much on really converting languages. And yeah, it's helping that it's based on the mature and widely used LLVM infrastructure, so there are not so many tools provided yet by the QIR Alliance, but whatever is missing and whatever we need, we can basically just develop as our own LLVM path. And yeah, some downsides there are. So the quantum instructions in the QIR are function calls, which means you cannot really do semantic checks directly on the IR level. But yeah, we can do that or test everything via our own full stack tests. But yeah, it could have been also a valid choice to define basically our QCCD instructions as a dialect in the MLIR. Then you would get these semantic checks directly on the IR level. But so far, we don't see a huge benefit from introducing this additional complexity into our software stack. We would if there would be some high-level optimizations that you can only do with this higher level language, then we will probably start looking into MLIR again. Maybe this will be the case for quantum error correction. Yeah, we're discussing this internally currently, and yeah, we will see. But for now, the ion shutting problem and the transpilation paths that we have can be very easily be done really on the LLVM IR level. So that's why we stick with that for now. And that was the talk already, so I hope I was able to give you a good overview of what QUDORA is doing on the hardware level and what this means for us on the software level. And yeah, these are the smart minds behind the hard work. So with Tobias, started looking or working on this quantum software field already a while ago. Basically, we started together. And yeah, Christian also joined the team a while ago, making sure that everything is connected and working nicely together, but also deeply involved in the compiler engineering part. With Nico, we did research on quantum error detection, and he's now doing his PhD on quantum error correction. Marius did his PhD partly on the noise model or of the NFQC technology, and he's also working on the compiler a lot. And yeah, at last, Hans is really our interface to the hardware. He's working on the real-time operating system, making sure that everything from our side of the software stack can be connected to the hardware. And yeah, that's it. And yeah, thank you for your attention.
Thank you, Daniel.